Hello everyone, welcome to Diagnostics by Rick. Today I will be discussing how to perform a relative compression test. This test allows you to use your oscilloscope and an amp probe along with the vehicle's battery and starter to perform a compression test on any engine. This can be especially useful on engines where a lot of disassembly is needed to access some of the spark plugs. As technicians, we like any trick that can save us some time. The relative compression test is one of the best time-saving test available to us. Sure, you might be able to check all 4 cylinders with a conventional compression gauge on some small engines very quickly, but many V6 and V8 engines can take several hours to complete a compression test on every cylinder. Compared to just the few minutes it takes to run a relative compression test, that is a lot of wasted time. First, I need to be clear that this is not measuring actual real compression in PSI or pascals. Instead, it is comparing the compression of each cylinder to the compression of each other cylinder. That means this test does have a weakness in that if all cylinders on an engine are equally low, then this test will not show it. If an engine is supposed to have 180 psi of cranking compression, and all 6 cylinders only have 100 psi, then the relative compression test will not show you a fault. But it will show you a problem when you have 1, 2, 3, 4, or 5 low compression cylinders. As long as you have at least one good one, this test will work properly. In fact, it will work even if all 6 cylinders are low, as long as they are not equally low, because it compares the cylinders to from one to another. So if you have 3 cylinders at 120 and 3 at 65, it will still work. When you turn the key and engage the starter, the current flow from the battery flows through the starter, causing it to spin, which then cranks the engine over. Anyone that has turned an engine over with a ratchet and a socket knows that it is not a smooth process. Every time a cylinder is on its compression stroke, it becomes more and more difficult to turn the engine, up to the point that max compression is reached, and then the piston starts moving back down on that cylinder again, making it easier to spin over once again. This image shows that as the piston moves up on its compression stroke, the amount of force needed to turn the crankshaft increases, which in turn causes the amount of current the starter draws to increase. Because we want to see what the starter is doing while cranking the engine, we don't want the engine to actually start or even attempt to start. So always disable it in some way so that the starter will still crank the engine over, but it will not actually start. On many vehicles, you can simply hold the gas pedal all the way down to the floor. This will put the system into clear flood mode, which turns off the fuel injectors. This does not work on every car, but it does work on quite a few of them, and it's the simplest way to disable it without having to remove any fuses. If that does not work, the best way to disable the engine is by removing power to the fuel injectors if possible. You want to leave the ignition system intact so that you can use spark as a sync to help you identify which cylinder is which on your scope capture. So always try to kill the injectors and not the ignition coils. We can use this to compare the amount of force needed for the compression stroke of each cylinder and then compare them to each other. If one cylinder is easier for the starter to push on its compression stroke than the others, it will show up in the form of less current draw. This capture is from a small block Chevy truck, a standard 5.7 liter engine, and you can clearly see 7 peaks and 1 missing peak. This truck had a misfire on one cylinder and had no or at least very low compression on that cylinder. But which cylinder was it? It is easy to tell from this picture that this is a V8 engine, but by this picture alone we have no way to know which cylinder is which. So how can we remedy that? Well, that is easy. All we have to do is turn on a second channel and attach it to a secondary primary ignition. If it is a coil on plug system, then connect to the coil control circuit for one of the ignition coils. It doesn't matter which coil you connect to as long as you know what cylinder number that particular cylinder is. Then just look up the firing order for the vehicle, and from there you can figure out which peak belongs to which cylinder. This vehicle still had an old school ignition system with a distributor and plug wires. I know you can see some ignition noise here from all 8 cylinders, but the longest red spike is the plug I am connected to with my test lead. It is connected to cylinder number 1. Now we look up the firing order, which many of you already know for a small block Chevy is 18436572, so we can use that information to number the other cylinders. It's pretty easy to see that the problem is with cylinder number 8. Looks like number 6 also may be a little lower than the rest, which could indicate a problem with it, but it's certainly not completely dead like number 8 is. I do want to point out a phenomenon that you will see almost every time you have a low compression cylinder. That is where the cylinder after the low one appears to have higher compression than the rest. This is actually normal and does not really indicate higher compression. Instead, what is happening is that the starter was able to get the engine spinning at a higher speed during the low compression event. So now, when the next good cylinder does hit its compression stroke, it's kind of like the starter hitting a brick wall. So current increases a bit when it has to work hard once again. So don't worry about this, it does not mean you have higher than normal compression. Here's another example with a 3.7 liter Jeep Liberty. The firing order is 165432, and I have channel 2 synced on the number 1 ignition coil for reference. So which cylinder is dead? Well, starting with our sync of number 1, we can number the cylinders and then count through the firing order and see that number 4 is the dead one. Within just a few minutes, we know that there is a base engine problem with cylinder number 4. This 5.7 Hemi brought up an interesting challenge in that I am synced on the number 1 cylinder, but if you notice, it fires twice every revolution and not just once. If you remember, this was the older system with 1 coil and 1 plug wire for each cylinder. Each coil would fire the cylinder that it was in, but it also had a plug wire that ran to the other side of the motor to its companion cylinder. So looking back at our capture, we are connected to the plug wire for the number 1 cylinder, but which spike is number 1 on compression and which spike shows it on its exhaust stroke? Well, if you ever used an ignition scope on older waste spark systems, you will remember that it requires more energy to fire a spark plug under compression than it takes to fire it on the exhaust stroke. That means the spike with most kV is our compression stroke, and the other one is the exhaust stroke. Since firing order is again 18436572, just like on the small block Chevy, then we know our low cylinder is number 2. I had a shop pull the valve cover on this one while I worked on another vehicle. If you look close, you can see the push rod is popped out and is laying down under the rocker shaft here. Although using an amp probe is a little easier, you can actually do the same test with battery voltage, so an amp clamp is not a must-have. The concept is the same, except that instead of watching amperage go up as each cylinder hits a compression stroke, you watch battery voltage drop down as each cylinder hits compression. This capture is from a Malibu. My sync this time is not spark, but rather an in-cylinder pressure transducer that is in cylinder number 4. The firing order is 123456. Remember, since we are looking at voltage, we are interested in how much each compression stroke pulls down battery voltage. So a weak cylinder won't pull it down as much as a good cylinder with high compression. We know we are synced on the number 4 cylinder with the in-cylinder capture, so we can number the cylinders by the firing order. Now look at the arrows. You can see that the cylinder immediately following number 4 barely pulls the voltage down at all as compared to the other cylinders. That is cylinder number 5. If we keep counting, you can see that number 3 is also low. This engine had a blown head gasket between cylinders 3 and 5, causing low compression on both cylinders. Also, make sure you crank the engine long enough to show a problem. Sometimes with valve and lifter issues, the issue may not be there when you first start cranking the engine, but will show itself the longer you crank. This 4.7 liter started out good, but the longer I cranked, the worst compression got on one of the cylinders. Sorry, no sync on this capture, but I do know that the problem was with cylinder number 2. I did get an in-cylinder compression capture of number 2 while cranking. Compression is as high as 150 and as low as about 100. It was very cyclical like this. As long as I continued to crank, it would keep going up and down every maybe 10 or so revolutions. As a reference, here's number 4 from the same vehicle while cranking. Look how nice and even and flat the compression is on this cylinder, maybe around 155 all the time. And here is number 2 while running. The symptom with this vehicle was a misfire that would come and go every few seconds like clockwork. It would slowly get a little bit worse, and then a few seconds later it would be gone, and then it would get a little worse, then be gone, rinse, repeat. The issue was a valve that was rotating in its seat, which it is actually supposed to do, but the valve did not seal as well in certain clock positions as it did in other positions, resulting in different amounts of compression depending on where the valve was in its rotation. Keep in mind that oftentimes a cylinder may only be a little low in compression and not completely dead, as was the case with this 5.3 liter GM engine. It is synced on number 1 and the firing order is 18726543. You can see a definite problem on cylinder number 7 and a potential issue with number 8 as well. Let's do a fun one to close this out. It was a 2005 Kia Sedonia. The shop had replaced both heads because the engine had been overheated. When I got there, the shop had a jump box and a battery charger connected to the vehicle. The battery was also brand new and had just been replaced. The problem was this engine sounds like it's cranking over very slowly, certainly not fast enough for the engine to catch and start. I did all the usual tests on the battery and volt dropping the ground and positive cables, and not only was there no appreciable voltage drop across the cables, but battery voltage wasn't even going below 11 volts while cranking. So why is this thing cranking over so slow? I decided to connect an amp probe so that I could use relative compression to see what the cranking speed was. My relative compression capture looks decent with no obvious major faults with engine mechanical. I use the cursors and measure 1.54 seconds for the engine to make 2 full revolutions. Remember, it takes 2 revolutions to get all the cylinders through a compression stroke. So 60 seconds divided by 1.54 is 38.96. Then multiply that by 2 and you get about 78 RPM. This engine is spinning way too slow. Perhaps the overheating damaged the bottom end, making it difficult to spin. Maybe a main bearing issue, or is this as simple as a starter issue? Something mechanical is going on to keep this engine from spinning fast enough, but I'm not sure what it is yet. So I added a sync and went ahead and put a pressure transducer in cylinder number 1. Do you notice anything wrong here? There are only 3 compression strokes. Half the engine is dead. Okay, so that means I calculated cranking RPM wrong. 6 compression pulses on the relative compression capture actually represents 4 revolutions of the engine and not just 2 because half the engine is dead. So our real cranking RPM is about 156. That's a little bit more normal. Since I know number 1 is good, and it looks like every other cylinder is missing compression, and firing order is 1, 2, 3, 4, 5, 6, so that means cylinders 2, 4, and 6 must be dead. So I connect cylinder number 2 so I can prove that it has no compression, but it does. In fact, it's pretty much the same compression as number 1. How can all 6 cylinders have compression, yet I only have 3 compression pulses on a relative compression capture for every 2 revolutions of the engine? That doesn't make any sense. Unless... Okay, before I say anything else, let's go back to our original relative capture and look a little closer. look at the difference between peak current draw when a cylinder is at TDC max compression and minimum current draw. It goes from about 100 amps all the way up to about 370 amps. Normal current will vary a fair bit depending on what kind of engine it is, but typically it's only around 50 or 60 amps. There's a 270 amp difference between compression and no compression. So either this engine has massive amounts of compression, similar to a diesel, making it very hard for the starter to work, or we have two cylinders hitting compression strokes simultaneously. That means each cylinder is hitting compression stroke at the same time as its companion cylinder, instead of one being on an exhaust stroke while the other is on its compression stroke. It turns out the machine shop had swapped the intake and exhaust cam on the driver's side head. The shop owner called the machine shop to see if he had removed the cams while checking the heads, and the machinist actually said, "It doesn't matter where the cams go because the lift and duration is the same for the intake and exhaust cams on this engine." To which the shop owner rolled his eyes and made the obvious comment, "But yeah, what about valve timing?" Well, that's all I have for now on how to do a relative compression test. I hope I have shed some light on the subject and perhaps saved some of you some time the next time you feel there may be a mechanical problem on the vehicle that is difficult to do a real compression test on. Earlier, I said that it's always best to remove power from the fuel injectors if possible. The reason for this is because you want to be able to use the spark to help you sync up the capture so that you know which cylinder has the problem. So why not remove a fuel pump fuse or a fuel pump relay, because that is usually easier? Well, because even if the fuel pump is shut down, there is still fuel in the rail and often there's residual pressure. This will cause the engine to spit and sputter a little bit as you crank it over. You can't have the engine making any attempt to start whatsoever, or it will drastically distort your results. You need the engine to spin over but not have any combustion events. On some vehicles, this can be a difficult thing to do because of how the system is wired. Removing a fuse for the fuel injectors may also kill the ignition coils, or it may kill the PCM and then your starter won't even engage. In these cases, look for a bolt connector maybe on the intake that may allow you to unplug the fuel injectors but not unplug the ignition coils. As a last resort, you can disable the fuel pump, but if you do that, make sure you crank the engine until it no longer makes any attempt to ignite any residual fuel in the system, and then do your relative compression test. If there's a fuel pressure test port, you can depress the Schrader to relieve any pressure in the rail to make this a little easier. If you've enjoyed this video, please hit that thumbs up button and don't forget to subscribe. Also, click the little notification bell and select all notifications so that you'll be notified when I upload a new video. If you'd like to help support this channel, I'll leave a link to my Patreon page in the description below. I'll also put a link to the Google Drive that I set up for my Patreon supporters, and I will probably put some of these relative compression captures that are in this presentation, maybe even a few others, so that you can download them. As always, thanks everyone, and have a good day.